All right. Well, hello, chemists. So welcome to the Sunday afternoon edition here of the A-level chemistry masterclass. Okay, so on this class, it's all right. Well, hello. Got to hit the mute button on the microphone. On this class, chemists, it is calculation day today. So what I wanted to do today was straightforward calculations. I did promise the end of the last master class, so what I would do is I would do pH calculations of strong acids, strong bases. I'll show you how the pH depends, the temperature. We'll look at the ion product of water, and then we'll look at dilution problems and how to calculate the pH of a solution made from adding an acid to a base. So without further ado, let's get down to it here and share the screen. If I can get my screen to share right here, hold on, like this. Okay, so should be coming in there. Right, here we are then, chemists. All right, so on this one then, this is where we left off last time, right? So where we left off last time, chemists, with this one, is that we said that the pH is minus the log of the hydrogen ion concentration. And what I wanted to do is I want to put in here at equilibrium, okay? And this bit becomes important. It's a reminder for when you're doing pH calculations of weak acids and weak bases, which we'll do next week. All right, so really, this is that equilibrium. Normally, you just see it as minus the log of the hydrogen ion concentration, okay? Then you've also got another way of looking at it, because chemists, students always ask me, they say, well, what does the P stand for right there? The P is just a mathematical function. It just means minus the log. And so you can take minus the log of anything. For example, you can take minus the log of the hydroxide ions if you were dealing with a strong base, right? And we know that pH plus pOH added together is going to give you 14. And before we forget, before we start doing some calculations, we've got Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration, okay? So on this one then, chemists, here we are, right? Yes, perfectly straight line there. I know there's a ruler option on bit paper. Students always want to know, well, how do you get such a perfectly drawn line? Well, because there's a ruler option on bit paper. Anyway, what I wanted to do is I did pull these off a worksheet, okay? Nothing special about them. So I wanted to do the monoprotic and I wanted to do a diprotic acid. Okay, so a quick review then. A monoprotic acid is, and we touched on this last time, HCl is an example of a monoprotic acid. Because can I get monoprotic to be written a little bit more neatly than that? I can. Monoprotic acid like this. Right, because you've got one ionizable hydrogen, an acidic hydrogen at the front there, okay? And the diprotic acids, if we're just dealing with strong acid and strong bases, all right, we'll do this one, your H2SO4. All right, this is a diprotic acid here. So this is my diprotic like this. And basically, I've got one acidic hydrogen listed at the front. Here I've got, this is my diprotic, I've got two hydrogens that can ionize at the front like this. And so this is my diprotic. Now, the reason I mentioned this one is that last time we did go over weak acid and weak bases, strong acid and strong bases, okay? And for the weak acids, the organic acids, it is slightly different because you need to look at the hydrogen ions that's attached to the carboxylic acid group, All right, not all hydrogen atoms are acidic. Anyway, the reason I mentioned this one is real simple then. Let's just have a quick look then at A. So first question you need to ask yourself when you're doing this chemistry is, are these strong acids? All right. And the answer is they are, because you went over these last time. You know, you got the hydrochloric, the hydrobromic, the hydroiodic acid, the sulfuric, the nitric, the chloric, and the perchloric, the 7 strong acids. You got the halo acid, you got the oxy acid. The reason why I mentioned that is because this equation here only works if it's a strong acid. So the first thing you have to do then is determine, is it a strong acid? It is. And so therefore you're going to say, and I'm going to do this live, pull up my trusty calculator here, which is actually, this is kind of humorous. My calculator is older than you are. So whoever's watching this in the replay or the live stream, just keep in mind that my calculator is it's a Texas Instruments TI-83 Plus. So it's older than most of my students. But anyway, look, I'm going to say minus, if I just do question 1, right, pH is minus the log of the H plus concentration, which is going to be minus the log of 0.2. Okay, so this is going to be, hold on, let me do this live now, right, minus the log of, what is it, 0.2? 0.2 means that my pH is, I've got 0.698. So I need to round this up to 2 decimal places, right? So pH is always reported to 2 decimal places. So if I round this up, this should be 0.70, right? And the reason why I can say this is because HCl, obviously aqueous, is going to ionize 100%, like 99.9%, right, to hydrogen ions and chloride anions like this. And so, yes, it's a 1-to-1 correspondence, which means that the concentration of hydrogen ions is the same as the concentration of the HCl. Nice, easy correspondence, right? Now, having said that, chemists, did I put down too many decimal places, too many significant figures? I think I did, right? It's only 0.2, right? So it's only 0.2. Right now, the reason why I mention that, chemist, is because, and these are going to be multiple choice type questions, all right? These are going to be type of questions that you see on the exam. It doesn't matter what exam board you're taking A-level chemistry, and there's going to be at the multiple choice section. They're not going to give you HCl. No, because that's too easy. All right, what they're going to do is they're going to give you something like, say, question 1C. All right, so question 1C is, I got 0.4 molar solution of sulfuric acid, right? So on this one, let me answer it like this. You go H2SO4 like this, okay? And arrow, right, like this, whoops, is, I know, kind of funny about my arrows, hold on. Because it's a strong acid, you can say the equilibrium position moves all the way over to the right. It's going to give you 2H plus and SO4 2 minus like this. Right. So this is the reason why they're going to ask you this on the exam, is because, right, you're going to write down 0.04 molar solution of sulfuric acid, and it's not a 1-to-1 correspondence. You can't put 0.04 directly into the pH calculation. What you need to do is you need to double it. It's a 1-to-2. So this is a 1-to-2 correspondence. So this would be 0.08. So now you can put it into the pH calculation. Now, chemists, what you're thinking then is this. When you start doing these calculations, when you start doing practice papers like past paper questions, right? just don't do them ad nauseum, like, oh, I've done a pack. No, you do 10, you mark it, and then you go back into the notes, and then you see, is there anything in your notes that's missing? You consolidate your notes, and then you move on, right? But also, here's my other test taking tip, is start to think like an examiner, meaning like a teacher. So when you see a question, just don't go, okay, out on 0.04 molar solution of sulfuric acid. No, ask yourself, what's the catch? Like, what are they really testing here? It isn't as if you can put a number into the pH calculation. No, what it is did you notice how the moles of sulfuric acid, the moles of hydrogen ion is 1 to 2. All right. So if I do this one real quick, what 0.08, then it comes back as I got 1.096. It means what 1.10. All right. Can you always report pH out to 2 decimal places, right? So pH 1.10. Now, also, chemists, what you should do is this: that you should have what I call a common sense check, because it's really easy to do these calculations on the calculator really quick. And then, the exam board is going to put down every tripwire they can think of in the answers, like what possible miscalculation could you have done, it's this one. Is start to think, does it make sense from a chemistry point of view? And the answer is yes. If you're talking about strong acids and strong bases, having a pH less than 7 would indeed make sense. So this was 1A and C, calculating the pH of the following solutions. Now, meanwhile, let me go and move my little video link over there. All right, is this one? Let me add a new page here, and let's run the process backwards. Okay, so on this one again, what I'll do is I'll do a monoprotic and a diprotic acid. So this time let's look at 2C, right? So 2C got nitric acid with a pH of 1.30. And so again, always got to make sure that we're using the correct formula, and the formula that we're using is indeed justified. And so I can say right here then, I was going to do the one with nitric acid, right? This one and this one, all right, is got to be, first question I always ask is it a strong acid? It is, therefore the equations I've written here are justified. All right, so nitric acid with a pH of 1.3. So I'm going to keep moving my little video link around here. All right, so 1C is what nitric acid what was the pH of 1.3, right? Was that right? Like this? It was, yeah, nitric acid, right? And so again, this one, chemist, look, these are kind of algorithmic, meaning that once you've done one, you've done them all. Think of it again. Now, chemists, look, here's my second exam taking tip here. My test taking tip is this one. Is start to templatize things as much as possible. Meaning, if you can come down with a strategy for answering a question and you can fine tune it, get down to a certain number of steps, and then after that, you just got to repeat the steps to get the correct answer to any question that you have, well, then this is the way to go, because I keep talking about bandwidth, right? You don't want to have, you don't want to look at a question and not have a plan in mind on how you would answer the question. And on the exam boards, they all tend to be really algorithmic. Like you've done one, you've done them all. So on this one then, nitric acid, strong acid, it's going to ionize. They don't normally ask you to put the equation state in, but I normally do. Why is just a habit. If they need it in the mark scheme, I've done it. If they don't need it in the mark scheme, well then, okay, no worries, just carry on. So pH of 1.3. So this is what I'm thinking. I always write down the equation here. It's a 1-to-1 correspondence. Okay, that's going to come in handy like this. 1-to-1 corresponds like this. Hold on. Can I write 1-to-1 a little bit better than that? Maybe down below. Look, 1-to-1. So if my pH is 1.3, then my hydrogen ion concentration, and again, I'm always in the habit, chemists, of writing down equilibrium, because when we talk about weak acids, it's going to come in handy. It's a mental note that you got to be at the very bottom line of the calculation here. So just habit. Hydrogen ion concentration equilibrium then is 10 to the minus pH, which is going to be 10 to the 1.30. And so, hold on my calculator here. 10, yes, to the 1.30. I got, ding, ding, ding. Oh, forgot to put in the minus sign on my calculator, right? That's, hold on. 10, right. Now again, chemists, I always do these live, right? And so how I knew I did something wrong with my calculator there is that I had a hydrogen ion concentration of 19. I'm thinking that does not make any sense at all. All right, so I had a quick look. Yes, forgot to put the minus sign in. All right, corrected that. So I got hydrogen ion concentration now is 0.05. Now, what I'm going to do is I'm going to take this out to 3 significant figures, okay? 0.0501, all right. I just looked at the number of significant figures appeared. In fact, let me take it out to one more. All right, I always like to take it out to one more significant figure than what's in the question. And so now I've got this, and I believe the question was calculate the concentration of the following acids. And so now, because it's a 1-to-1 correspondence, if I go over to orange here, right? Call this Syracuse orange. If you follow American football, all right, then, Syracuse football, never mind. All right, 0.05012. 1-to-1 correspondence means that this is also 0.05012 like this. And so there we are. Go back to royal blue. And so I'm going to say that my concentration of nitric acid is going to be 0.05. I'll just take it out to 3.0501. Done. All right. So this was this one. Now, the other one that I wanted to do, chemist, was this one here. All right. The other one I did was the one with sulfuric acid. Now, the one with sulfuric acid, pH of negative 0.50. So hold on. Sulfuric acid with a pH of negative 0.50, right? 0.50. Now, the reason why I picked this one, Gims, is twofold. Is number one, you're looking at the pH, you're saying, hold on, you what? I learned the GCSE, it was only the pH was 1 to 14. Oh no. You can go down below 1, because you can have what's known as a superacid. Okay, so for example, it's not a superacid, but like say battery acid is like very, very low pH. Okay, or you can have, I think the superacids are the one with it's aqua regia. If you want to look it up, all right, you can't say aqua regia. I think it's a mixture of like nitric and sulfuric acid. Okay, it will actually dissolve gold. Or the other one is you can have a super base. You can go beyond 14. You go up to about, say, 16, okay? So anyway, put this one in here just to be able to tell you that you can have a pH that's out of the range of 1 to 14. That is totally acceptable. But I also did this one, chemist, because this is one that you're more likely to see on the exam in the multiple choice section because, well, it's a 1 to 2 ratio. Go back to Syracuse Orange again. Look, it's a 1 to 2 ratio, chemists, like this, 1 to 2. So we've got to take this into account when we get the concentration of the acid, right? So having said that, here we are. So I say, right, pH is equal to negative 0.50. And so my hydrogen ion concentration at equilibrium is equal to 10 to the minus 0.50. Hold on, I can write minus 0.50 a little bit better than that. Okay, all right, because my pH, chemist, was negative. We get negative pH in this one. This is why it's going to be like this. All right, and so let's see. The hydrogen ion concentration then is going to be, let's take a look right here, 10 to the 0.50, the double negative comes into account. I got a pH of what, 3.16. I mean, the hydrogen ion concentration of a decimals, but high, hold on. I got 3.16. Hold on. All right. So let me see, hold on, if this actually works out. All right, so 3.16. Okay, so yeah, that's right, negative 0.50. All right, 10 to the negative pH. So you put in the negative 0.50, double negative comes out. Hydrogen ion is 3.16. All right, now it's a 1 to 2 correspondence. All right, so the concentration of my sulfuric acid. Okay, try to get this written a little bit more clearly. The concentration of my sulfuric acid then is equal to the concentration of my hydrogen ion divided by 2. Right, 1 sulfuric acid over here. It's a 1 to 2 correspondence, okay? Right. So yeah, the concentrations cancel out. And so I end up the sulfuric acid concentration divided by 2. I got 1.58. All right, 1.58 like this. All right, moles per decimeter cubed. Okay, then, so we're 2 for 2. All right, so strong acids. All right, just pH calculation and get the concentration going. So this was these two types of questions done here. All right, now we're coming down to this one. Oh, this one, right. So question 3, the other one I said I'd do last time is I drank the afternoon tea or chemist. The other one I thought we'd do next time is the dilution. So how I look at it is this one, right? You know that concentration is moles over volume. You go, right. So therefore, moles is concentration times volume. Right. Now, if you dilute something, the moles that you have initially, as in before you diluted it, must be equal to the moles you have after you've diluted it, because you didn't change the number of moles. The only thing you've done is you changed the volume. Right. So therefore, if I put this equation here and for this, I can get concentration initial, volume initial must equal concentration final, volume final. And you've probably seen this under so many different formats, okay? Like, you know, C1 V1 is C2 V2, don't know. So having said that, chemists, here we go, this one. All right, so let's see, the calculated pH solution is formed the following way. Right, let's take a look at A then. We'll start off with A. Yeah, we'll do nitric acid again. All right. So let's say I've got addition of 250 cubic centimeters of water to 50 cubic centimeters of 0.2 mole a decimeter cube nitric acid. So if I'm on 3A, right, I'm going to do concentration initial, volume initial is concentration final, volume final, and that asking for the pH. And so what we need to do, the game plan is this, right, chemists, is that we need to get the final concentration of hydrogen ions and then put that into the pH formula. It's a really easy calculation. The only difficult bit is they're trying to get you muddled with the volumes, all right? But they're not going to do that because we know how to handle this. Right, concentration initial, volume initial over volume final, which is my concentration initial was what, 0.2. All right, so 0.2 like this. And the volume initial was 50 cubic centimeters, right? So I've got what, 50 cubic centimeters like this. And the volume final on this one, chemist, all right, they're being a bit tricky with the question. It says addition of 250 cubic centimeters of water to 50 cubic centimeters. So volume final would have to be 300, right? But the 50 started with and the 250 that they added. All right, so the concentration final then would be, well, let's take a look. So I got 0.2, my trusty calculator, 0.2 times 50, yes, divided by 300. And I got 0.033. So again, what I'm going to do is I'll just take it out to 4 decimal places. I always like to carry one other digit. Okay, I always like to carry one extra digit when I'm doing the calculation. So I totally avoid round off error, and then we could fix this at the end. All right, so the concentration of final is 0.0333. So therefore, the hydrogen ion concentration, the final hydrogen ion concentration, must be 0.0333, like this. Now, because it's a strong acid, it's nitric acid, the pH is minus the log of the hydrogen ion concentration, which is minus the log of, hold on, 0.0. Let me write just a plain old bracket like this, 0.03333, 1, 2, 3, 4. Right, which is, to put this in the calculator, let's do it live, minus the log of 0.03333 is coming back as 1.48. So you need to have 2 decimal places, 1.48 as my pH. And I asked myself, does that make sense? Yes. Why? Because it's an acid, it's a strong acid, it's got to be below 7. All right. If I had something weird, like above 7, you think, that doesn't make any sense. All right. So here's this one. And let me try a diprotic acid again. And on this one, we will do, let's do B. All right. Again, chemists, once you've done one, you've done them all. All right. So here's my one for 3B. Hold on. So C initial, volume initial, C final, volume final. So the concentration, the final is C initial, volume initial over volume final, which is, okay, 0.1. Like this, and it was 100. 0.1. It was 100 cubic centimeters. Because the volumes cancel out, I don't need to convert to decimeters cubed. It's just a ratio. But again, it's going to be 25 and 100. So it's going to be 125 on the bottom. The volumes are obviously additive. And so the concentration, my final concentration is going to be, let's see, 0.1 times 100. All right, divided by what, 125. I got 0.08, like this, 0.08, which is equal to my, it is equal to my hydrogen ion concentration, right? So right here. Hydrogen ion concentration is equal to 0.08. It's my final concentration, right? And so therefore the pH is minus the log of the hydrogen ion concentration, and put these in, and I'm going to get minus the log of 0.08 is going to come back as 1.10, right? 1.10 done. Okay. Now, question is, oh no, I did need to double it. I'm thinking now, do I need to double that one? I got 0.1 mole. Yes, I did need to double it. Oh, well, you know, we do these live because it is 0.1 mole of sulfuric acid. Yeah, so so what I should have done is I should have doubled it. I'll do that now. Yeah, this one is 2H plus and right, SO4 2 minus. And so yeah, this was 0.1 mole. I'll buy that. But the concentration of the hydrogen ion was actually 0.2 because it's the 1:2 ratio like this. So I just needed to make this to be 0.2. So let me correct that real quick, and then we can move on to something else. All right. So yeah, this is double. So if it's the concentration of the acid was 0.1, the hydrogen ion would be 0.2 because it's doubled like so. All right. And then I'm not liking how that looks all of a sudden. I know. 0.200 times 10. No, it was 100, right? Yeah. Right. So let me correct that real quick. Hold on. So we've got 0.2 times 100 like this. Yeah, over 125. I got 0.16. Yeah, we just doubled this. This 0.16. Final concentration, this is 0.16. And so therefore this is going to change slightly. Hold on. 0.16. And so minus the log of 0.16 is coming back as, all right, it just dropped down to 0.80, all right? Slight drop of 0.80, okay? So anyway, this was this one. All right, so we did strong acid calculations and strong base, we did the pH of strong acid, the concentration of an acid solution given the pH. We did dilution problems. All right, so here we go with this one then. Ooh, this one. Yes, I did promise you, chemists. I did promise you. Did I miss something out here? No. Okay. All right, hold on. I did promise you this one. The one with the KW of water at a different temperature. All right, so this one, chemists, they do enjoy putting this on the test. They just do. All right, so it says calculate the pH of water 40 degrees when the KW is this. All right, so a quick review. Did we not say that water is amphiprotic, meaning that it can act as an acid and a base. And so you're going to have H3O plus and OH minus ions because, right, you've got the PT, the proton transfer, all right, because we're assuming that water, it's amphiprotic, but we're thinking, we're using the Bronsted-Lowry definition of an acid and a base, right? So we're thinking that this is endothermic. And so we did this last time. Delta H is going to be positive. It's endothermic. And how I teach it is this, is put in the triangle on the left-hand side because it's acting like a reactant. You're adding heat in, yes, to go break the bonds in order to form the H3O plus and the OH minus. So the Kw then would be equal to, the Kw would be equal to, now I'm just going to write it as H plus times OH minus like this, right? Because this is how you normally see it in the textbook. You normally see it as H plus. All right, so anyway, this one here. Now, I said calculate the pH of water. So I'm thinking, now, would you agree, chemists, that there's a one-to-one correspondence between the water molecule that is acting as a base and giving you the conjugate acid, and the one that's acting as the acid and giving the conjugate base, right? So in other words, you're thinking, yes, there's a one-to-one correspondence. So we can now say the Kw at a given temperature is temperature dependent. Now, look, this is a tie-in because when you did equilibria, all right, you did Kc and maybe you've done Kp, you're thinking the only factor that can change the value of Kc, Kp, or Kw is the temperature. All right, so you're thinking because they changed the temperature down to 40 degrees, it's not, Kw is not going to be equal to, it's not going to be equal to 1 times 10 to the minus 14. And so what they're playing at, chemists, here is this bit. Again, look, they're just trying to get you confused as to thinking, right, I thought that Kw was 1 times 10 to the minus 14. No, Kw is 1 times 10 to the minus 14 at 298 kelvins. Okay, this is not a 298 kelvins. And so because of that, the value of Kw is changed. So we got 2.09, all right, times 10 to the minus 14 is equal to H plus times OH minus. Now, chemists, this is a bit, I've seen this in a lot of mark schemes. I don't really agree with it, but what they say is all of a sudden they call this X squared. What they should say is the H plus concentration is equal to the hydroxide ion concentration, which is equal to X, because it's the same. And so now you can call this X squared. And if I put this in with the square root of what, 2.09 to the negative, hold on, 2.09 to the negative 14 is going to be, I got what, 1 point. So look, X squared, if I solve it for X real quick, X is going to be equal to 1.45. Let's see, how many do we need? Let's do 1.4457. Take it out a few more digits, right? Times 10 to the minus 7, right? Which is equal to the hydrogen ion concentration, which is equal to the hydroxide ion concentration, right? Now, having said that, you're thinking, what they want to know is the pH. Well, the pH, if I do a sidebar right here, right, the pH is minus the log of the hydrogen ion concentration, which is minus the log of 1.4457 times 10 to the minus 7th, which is, if I do the negative, the log of this, hold on, 1.4457 to the negative 7th, I've got 6.84. Right. I said, oh, hold on a minute. Are you telling me that the pH of water is not always 7? Yes. Are you telling me that the pH of water changes pH depending on the temperature? Yes. But now this is the bit, chemists. They're going to ask you this and say, is the solution still neutral? Is the solution neutral? Okay. Now, again, you got to stop and think like a teacher, right? You're thinking, what do they mean? Is it neutral? Now, most people think that if a solution is neutral, it's going to be pH of 7. No, if it's a solution is neutral, what it means is that the hydrogen ion concentration is equal to the hydroxide ion concentration. This is what being neutral means, right? It just so happens that because we always use a temperature of 298 kelvins, 1 times 10 to the minus 14, the value for kW, then the pH comes out to be 7. But you're going to have a pH lower than 7 if you increase the temperature, but the solution is still neutral because the hydrogen ion concentration is equal to the hydroxide ion concentration. So it is still considered neutral, still considered to be neutral. All right then, chemists. So you're thinking, right? Now, do you see like the slight difference there, right? They're trying to trick you now on like how well do you know the concept and playing around with quality of language. But no, we know neutral means the hydrogen ion is equal to the hydroxide ion. The concentrations are equal, and so even if you are at a pH lower than 7, you can still be neutral, right? So this one was easy. All right, let's see what else we got. Look at the time here. Okay, we've got time to do these. Talking about, let's have a look at base calculations then. All right, so a strong base. And so again, look, to get my T here. Chemists, you're thinking, is this a strong base? Yes. Because didn't we say that a strong base was the group 1 hydroxide or the group 2 elements, barium, calcium, and strontium hydroxide, right? You're thinking, yes, it is. Right, so we'll do this one. Again, this is 1A. And so I have, let me try to get this going just like this. This is 1A log. So I got potassium hydroxide arrow. All right, because it's a strong base, it's almost 100% ionized, like 99.9% ionized, right? So K plus and OH minus like this, right? And so, right, 0.15 molar of potassium hydroxide would correspond to 0.15 molar of the hydroxide ion. And so on this one, the really fast way of doing it is you say OH minus is equal to 0.15 molar. Now, I know you can do the POH is negative the log of the hydroxide ion concentration, yes. And then pH plus POH equals 14, true. Or you can do this. You can say the hydrogen ion concentration, because you're writing Kw is H plus times OH minus, all right, you can say the hydrogen ion concentration is equal to Kw over the hydroxide ion concentration, which is 1 times 10 to the minus 14 over my hydroxide ion concentration is what, 0.15. And so my hydrogen ion concentration is, hold on, right, 1 E to the negative 14 divided by 0.15 is, I got what, 6.6, hold on, 6.667 times 10 to the minus 14. And so, sidebar, hold on, get the perfectly straight line there. And so therefore the pH would be minus the log of the hydrogen ion concentration, which is what, 6.6667 times 10 to the minus 14, which is going to be I got 13.18. Now again, can we see, does that make sense? Well, yes, it's a strong base, so therefore the pH must be greater than 7. Okay, so this is this one. And I tell you what, let me do one. Let's do 1C. All right. Let's do 1C like this one. Okay, so on this one here, a 1C. I'll do this one because again, it's a 1 to 2 correspondence. All right, so you got barium hydroxide, arrow goes to barium 2 plus and 2 hydroxides. And so, yeah, this is what, 0.2. And so 1 to 2 correspondence would make this 0.4. And so therefore, you're thinking, again, take the fast route to get it. H plus is equal to 1 times 10 to the minus 14 over 0.4, all right, which is equal to 14 divided by 0.4. I've got 2.5 to negative 14. And so, hold on, H plus pH. pH is minus the log of the hydrogen ion concentration, which is minus the log of what, 2.5 times 10 to the minus 14, which is minus the log of what, 2.5 negative 14. That's the log of what, 2.5 to the negative 14, and it's coming back as what, 13.6. 13.60 to be precise. Okay, so same idea with calculating the pH of a strong base, right? You get the hydroxide ion concentration first, and then you put it into the Kw expression, which is H plus times OH minus, solve it, and then get the pH out, okay? So I tell you what, yeah, I think we're fairly, let's just do one of the concentrations, the following bases, because I think you got the idea. All right, but let's just do one more. So I tell you what, let me move my video link over to the, I have to keep moving around everywhere. so you can see what's going on. All right, so let's see. All right, let's do one more. What the barium hydroxide with a pH of 12.50. All right, so hold on. Right, barium hydroxide, okay, with a pH of, was it 12.50? Is it 12.5? 12.50. Okay. All right then. So on this one, then you're thinking, right, what I would do is I would say, write down pH is minus the log of the hydrogen ion concentration at equilibrium. And so the concentration of the hydrogen ion must be 10 to the minus pH. And so the concentration of the hydrogen ion is going to be 10 to the minus 12.50, which is equal to, right, hold on, 10 to the minus 12.50 comes back as, I got what, 3.1623 times 10 to the minus 13, right? So I got this information from the pH, right? Now, having said that, you're thinking, I now need to get the hydroxide ion concentration. So the hydroxide ion concentration is going to be Kw over the hydrogen ion concentration, which is 1 times 10 to the minus 14 over, hold on, was it 3.1623 times 10 to the minus 13, which is 1. See, I have to do these live, chemists, they do, so that, you know, I'm just not reading off a script here. This is actually live, mistakes and all, whatever goes on happens in the hour is what actually happens in the hour, right? So, oh, one extra parenthesis. So 1 second button, E to the minus 14. All right, this is my Kw divided by 3.1623. Second button, E to the minus 13. No, I got it. Right, I got the OH concentration being 0.0316, and I'll take it out to one extra significant figure than what I need, right? So this is my hydroxide ion concentration, but, and this is the reason why I picked this one, chemists. Look, what they want is the concentration of barium hydroxide, right? The concentration of barium hydroxide? Yeah, it was. I mean, had to check. Goes to barium 2 plus and 2 hydroxides like so. So this is the concentration of the hydroxide like this. There is a 1 to 2. Let me change colors to Syracuse orange here. Look, there's a 1 to 2 correspondence. And so I'm going to have to half or divide by 2 the concentration of the hydroxide ion, right? So if I do that, right, divide that by 2, I only get 0.01, and I stick it to 3 significant figures, 0.0158. All right, molar. All right, so this one, a little bit more tricky, chemists, okay? It's the same idea as you did for the strong acid, getting the concentration of the strong acid, right? But it's more, there's one extra step involved. You got the pH, which you had to convert to hydrogen ion concentration, and then you had to get the hydroxide ion concentration, and then you had to get the concentration of the strong base. Yeah. So this one. All right. And let's see, what else did I have? That I have lined up? Okay, these. All right, chemists. It looks like, because I did want to do some past paper questions. I may have to do the past paper questions next time. All right, because I did promise you that I'd do some past paper questions. But here we are. All right, we'll do at least one of these. All right, so we'll probably end on this bit then. All right. Calculate the pH as the solutions form the following way. All right, so hold on. Isn't this am I just, yeah, oh, well, we've done this. Okay. Don't know why I put the page in there. All right, then. Okay, so we'll do this one. These right here, chemists. All right, we will end on this, but then, right, so here we are here. All right, we'll do question 2, and like next time we'll do question 3, right? So here's my these are pH of solutions of, well, basically a mixture of an acid and a base. Okay, strong acid, strong base. All right, so here we are then. Can move my video link out the way here. Calculate the pH solution when 25 cubic centimeters of sulfuric acid, to got what? Sulfuric acid, H2SO4. Okay. All right, is added to sodium hydroxide. The very first thing I'm going to do is write a balanced chemical equation. All right. So on this one, then, this is question 2. All right. Well, you know, from GCSE chemistry, you know this is going to be what salt, what sodium sulfate, and two waters, acid plus base gives you salt plus water. So I need what, 2 of these to make everything balance out. The very first thing I do then, chemists, is I write down the balanced equation like this. Now, on the exam, sometimes they do give you the equation and sometimes they don't. All right, so, and then I always write down, this is just a habit, CNV, concentration moles volume, CNV, concentration moles volume, all right? Let's say got 25 cubic centimeters of, I got what, 0.150 molar sulfuric acid is added to 50 cubic centimeters of 0.100 molar sodium hydroxide, right? So plan. Well, number 1 is I'm going to calculate the moles of acid and base. It's a really simple plan. Calculate the moles of acid and base present initially. So let's see, well, you know, concentration is moles of the volume. So moles is concentration times volume over 1,000. So let's say I'll put down what moles of acid is going to be what 0.150 times 25 over 1,000. Okay, which is, let's see, 0.150 times 25 divided by 1,000 is 0.00375 moles of acid, right? Moles of acid. And then you're thinking, my moles of base. Same exact logic. It's going to be 0.100 times 50 over 1,000, which is going to be, hold on, 0.1 times 50 divided by 1,000. You pass up 0.005, 0.005, like this, yeah? Right. Now, you're thinking then, right, next step is, well, which one is in excess? Hold on. I'm gonna have to delete this one because, oh, I know, I just need one extra page. I'll have to do this one next time, right? Chemist, I want to just delete it. So question 2, calculate calculate how much acid or base is left over, because you know it's going to neutralize, right? Well, so let's see which I got 0.00375 and 0.005. So it's going to be moles of base is 0.005, like this, 0.005 minus 0.00375 minus 0.00375. And let's see now, hold on, this minus 0.00375. I got 0.00125 moles of base left over. Like so. All right. Yeah, ding, like this. Yeah, did I get that right? Yes, looking about right. Okay. Now then, you're thinking part 3 is get the pH. Oh, hold on. Calculate the concentration of the hydroxide ion. Let's do this one first, right? So, chemists, look, this is the only tricky bit. The concentration of hydroxide ion there is going to be number of moles 0.00125 over. Now, volumes are additive. And so you've got 50 and 25, right? You've got 75. So hold on. All right, so I'm going to put down, this is moles. So you know where this came from, right? Moles. And you got what, 50 and you got 25 like this over 1,000. You've got to convert the decimal units cubed. And so we've got this divided by, right, 50 and 25. Let me do this. 50 and 25, yeah, divide that by 1,000. And so, right, just you see exactly where I'm coming from. 0 is 0. 125 over, I had this be what, 0.075, which means that I've got 0.00125 divided by 0.075 is, right, the concentration of my hydroxide ion is 0.01667. Yeah. So the only trick is, chemists, is that you had to divide by the total volume. And you know the Kw is H plus times OH minus. And so H plus is 1 times 10 to the minus 14 over 0.01667, which is, hold on, 1 to the negative 14. 1 second e to the negative 14 divided by 0.01667. I've got well, 5.9 9 times 10 to the minus 13. And so, yeah, it's going to be obviously basic. So pH is going to be minus the log of this. Which is minus the log of what, 5.999 to the negative 13 is going to come back, chemists, as being I got 12.22. All right, hold on, pen. 12.22. All right. So anyway, chemists, yeah, we did run over a little bit today. That's okay, you know, a little bit of extra from me. That's all right. So next time, what I want to do next time, chemists, is I wanted, let's do the next question here. I think it was question 3, right? And then we'll have a look at weak acids and weak bases. I'll introduce you to the concept of ice tables. All right. And that's what we'll do next time. All right. So everybody take care. Have a good day. And I will see you next time.